Thank you very much for the introduction. Today I will give a more theoretical lecture. So I hope it will be like understandable. So if you don't grasp something that is here, please let me know. So I prefer to, answer questions before everything becomes too hard. So I will talk about quantization of polaritons in confined structures. We've been working on polaritons for many years now, also with the group of Basia Piętka, who are doing experiments. But with polaritons, I mean in particular exciton polaritons. So polaritons which exist in semiconductor structures. I will show some introduction to these systems and how we can take advantage of the quantum nature of these polaritons. So I would like to first say about my collaborators on this project. So Amir Rahmani and Dogyen Ko are postdocs in Institute of Physics, and Maciej Dems is a professor at Łódź Institute of Technology, and he is responsible for the numerical code. So first I will give a short introduction to exciton polaritons. So exciton polaritons, as I mentioned, are quasi-particles that exist in semiconductors. Exciton is a particle which is basically a bound state of an electron and a hole. So imagine that, for example, a photon comes to the crystal structure. It excites an electron, which is also accompanied by excitation of the hole. But if the energy of the photon is too small to completely make this electron completely free, a bound state may form. And this bound state will be, in many respects, similar to a hydrogen atom. However, of course, the energy scales are much different, because usually here we are talking about binding energy of let's say, a few electron volts. Now, if we want to create a polariton, it means that we want to have a condition of strong coupling between these exciton-matter excitations with photons. Typically, the photon modes that are coupled to these excitons are modes of a cavity. So here is a picture of a microcavity, which is composed of 2 Bragg mirrors. And each Bragg mirror is basically a periodic collection of dielectric layers, which has the property that it has very high reflectivity for a certain wavelength. So this reflectivity can be really very high. So the quality factor can be up to hundreds of thousands. So it means that the probability for the photon to escape through the mirror is like 1/100,000. And under these conditions, it may happen that the decoherence related to the decay of photons and decoherence of the excitons is smaller than the coupling strength between excitons and photons. So the coupling strength, on the other hand, comes from the fact that every now and then this photon can excite at the exciton, and the exciton, on the other hand, can emit a photon. So, and if this energy scale of this process is higher than the energy scale of the decoherence process, we enter the regime of strong coupling, where the proper quantum description, the eigenstates of the system, are basically hybridized states of excitons and photons. So no longer we should speak about excitons and photons, but we speak about exciton polaritons as basic excitations of the system. The simplest Hamiltonian that describes this coupling is shown here. So we have 2 excitons, with operator A, photons with operator B, and we have coupling between them. And for the excitons, we can assume usually with a very good approximation that these are bosonic excitations, because these are excitons have integer spin. So at low density, they will have bosonic excitation commutation relations.
So I understand that if there is only single exciton excitation, it's equivalent to James-Cummings model with two-level atom, yes?
Yes. So if we have a system where we have room only for one excitation, so we have only one exciton mode that can exist, then this will be a James-Cummings model. But because here we can excite these excitons in many modes, spatial or momentum modes, we get more like a bosonic excitation. Okay, so now if we assume that this A and B are bosons, then we can find very easily eigenmodes of this Hamiltonian, and they are given by eigenmodes of this simple 2x2 matrix. So what do the dispersion look like? Usually photons and excitons have very different dispersions. But maybe I should say how it is, what I plot here. So you know, these photons which are in the cavity, they have fixed kind of fixed momentum in this plane, because this is like a standing wave mode. But they can have momentum in the perpendicular directions. So now if we want to plot the energy of the photon in terms of this perpendicular direction momentum, it will be like a quadratic dispersion close to 0. So photons become like massive particles in a cavity. Of course, excitons also are massive particles. However, it turns out that the mass of excitons is much, much higher, orders of magnitude higher than the mass of photons in a typical setup. So we can treat this exciton energy as more or less constant. So now if we couple these two modes together through omega, we will get two branches of eigenmodes, lower and upper polariton, which are marked here. So you can see that these modes also have some mass. And what are the properties of polaritons? Well, they are kind of like composite matter-light particles, so they will have properties of both light and matter. So they have excellent transport properties and extremely low effective mass, thanks to this photonic component. And on the other hand, this matter component results in very strong interactions. And actually, this leads to the strongest ultra-fast optical nonlinearity that exists. On the other hand, polaritons have relatively short lifetime, so up to, let's say, a few hundreds of picoseconds, mostly because these mirrors are not perfect. So even if I said they have, you can have a photon bouncing hundreds of thousands of times, every now and then a photon will decay, and this will lead to this short lifetime of polaritons.
So when you compare this lifetime of exciton and photon, so what are the orders?
So for example, usually it depends on the particle system, sample, and so on. But for typical microcavities, the photon lifetime will be, the photon lifetime will be of the order of picoseconds, maybe a few picoseconds, tens of hundreds of picoseconds, and the exciton lifetime will be usually in the nanosecond regime. But it depends on the details of the system. So now I will go to the problem of quantization of polaritons, as it was initially proposed by Hopfield, who actually proposed also the existence of polariton particle in this paper from '58. So he considered this interaction between excitons and light, and proposed that these normal modes of these light matter systems are linear combination of light and matter modes and their conjugates. So in terms of theory, He started with the Lagrangian, which includes the electromagnetic field, matter polarization, and coupling between them. And he found that normal modes eigenstates of the system are composed of operators for the electromagnetic field, for the polarization field, so polarization I mean the matter field, and also conjugates. So these are actually Hermitian conjugates, but back then it was maybe this notation was used also to describe conjugates. So in the end, in a system which is translationally invariant, you have such a matrix, and which describes these modes, and in the rotating wave approximation, it reduces just to this upper left corner, which corresponds to the matrix that I mentioned before. So that's very good, but this model actually is valid as long as we have translational invariance, or as long as there is a single spatial mode, or basically the modes of the photons and excitons have the same spatial distributions. So the question is, what happens when we have another situation? So an example of another situation is shown here. So here you have a picture of a microcavity, so just as I shown before. But here these excitons can be created only in a limited volume of inside the microcavity. So it means that the exciton modes will be limited to this small region, whereas photon modes will be plane waves which can propagate in all these perpendicular directions. So to solve this problem, I need to take a step back and now look at what has been done in the past in terms of quantization of photons in the electric structures. And I will briefly show the results of this paper by Roy Glauber and Maciej Lewenstein from '91, which exactly consider this question. So the starting point is that we have some system described by Maxwell equations, but the relation between D, the displacement vector, and the electric field is given by some dielectric constant, epsilon, which depends on position. So the system is not homogeneous. So we can then transform the system of equation to a single wave equation of this form for the electromagnetic potential. This system can also be written down in the Lagrangian formalism, which is shown here, where you can see that the electric constant appears here. And of course, we can, from this Lagrangian, we can also obtain the Hamiltonian function, which looks like this. And it turns out that this is a Hermitian problem, and we can find normal modes of this system, which are given by such an equation. So now omega is the frequency of the mode. And we can, these modes additionally have to fulfill this condition. And because this is a Hermitian problem, these modes are orthonormal, so they fulfill this orthogonality condition. So you can see that it looks like a normal orthogonality condition, but we have additionally some kind of kernel here, which is related to the dielectric constant. And now the idea is to take these functions, these solutions of the wave equation as a basis for our quantum modes. So we introduce coordinate operators Q, and we have this, we rewrite this vector potential operator in terms of these operators and the basis functions. Analogously, we can find momentum operators, and our momentum in the Hamiltonian function, which appears here, is given by these momentum operators. And it turns out, after some calculation, which is done in this paper, that this coordinate and momentum operations have such a form where these coefficients u, k, k are given by some kind of overlap formula where we have the basis functions. So you see that this is not the normality condition, because here we have stars in both of these functions. So u, k, k are not just a simple delta function. So in the end, the final result is that if we perform this transformation, our system can be diagonalized, and it is basically a set of harmonic oscillations with some frequencies omega k. And each of these modes correspond to these basis functions k. So basically, still in the dielectric, just as in free space, we can find a set of normal modes, which are harmonic oscillator modes. So what is also important that we can now write down the physical quantities operators, such as vector potential, electric field, magnetic field, which have quite simple form in terms of these basis functions and the operators of our modes. So now, so are there any questions? Maybe because.
So can you just simply mention how this reduces to vacuum? So we just put
yes.
epsilon to 1, and
yes, of course.
Everything
so in vacuum, we don't have this epsilon function. And also our basis functions that are solutions of the wave equations are just plane waves. So what happens is that this ukk will be simply a delta function, but delta function with k and minus k. And so then we get this formula. So you can see that we have this operator is a combination of k mode and a conjugate of minus k mode. So which is basically what you get here in this formula. But if you have this dielectric constant, it might this additional term may have a contribution of very many modes. So it's not just the minus k mode which will contribute with the to the normal mode. Yes, and then of course, because our modes are plane waves, then we will have just standard formula, like textbook formula for electric field in terms of operators. So this will be just e to ik r and e to minus ik r. Yes, so now I will go to quantization of polaritons. And I will use the results of this paper that I described to quantize this system. So what is the goal? Well, we have a weak coupling regime where we do not have polaritons, and we have this strong coupling regime where we have polariton eigenstates. And we also have homogeneous medium and inhomogeneous medium. In the case of weak coupling and homogeneous medium, we have just plane wave quantization of Maxwell equation that is done in every, quantum optics textbook. In the case of inhomogeneous medium, we can quantize photons according to this paper, and in the case of homogeneous medium, we have polariton modes described by Hopfield. So now our goal is to see what happens if we have inhomogeneous medium and strong coupling. Okay, so this is the system that we are considering. So we have Lagrangian, which includes both the electromagnetic field, the matter modes, which are modeled as harmonic oscillators. So this corresponds to our excitons. And we have some coupling between them, standard dipole coupling. And of course, we can find electric field, magnetic field. We can find also momenta corresponding to these variables used here. So this Lagrangian leads to a set of equations for Maxwell equations coupled to matter. And the solutions of these equations must fulfill this set of equations. So again, we have a wave equation, but also we have an equation which is like a resonant driven resonant oscillator solution. So we can see that we now can see that this alpha is basically the polarizability of the medium. Okay, so but this is let's say equations in the classical limit. And now we are looking at we want to quantize this system. So now first, to perform this canonical quantization, we find Hamiltonian. So we find this how Hamiltonian looks in terms of our variables. And in the absence of coupling, so if there is no this electromagnetic and matter interaction, this system, this part corresponds just to this case considered by Glauber and Levenstein. So we know that it has a solution which is a set of electromagnetic normal modes, which are harmonic oscillators, and that the electric field is given by a simple formula. Now, if we look at the matter mode, it's just a set of harmonic oscillators. So we know that it also can be described by this Hamiltonian. So now the question is, what happens if we add this interaction between matter and light? And this interaction adds some quadratic terms to the Hamiltonian. So you can see that all terms here are quadratic in terms of pi, a, and x. So now to find this eigenmodes of the system, I will use Bogoliubov transformation. So what is a Bogoliubov transformation? One can imagine this also in the classical limit. So let us consider that we have a harmonic oscillator. So this is just a system and particle in a potential, harmonic potential. We know that its solutions are just given by this oscillating modes. And now if we change the potential, so we want to move from this system to this system, we have to, and we want to find now the eigenmodes, we need to perform some transformation. And this transformation is given by such a formula. And to preserve the phase space volume, so that this transformation is canonical, a condition is that the surface of this circles is equal to surface of this ellipses. So it means that we will squeeze the system in position and extend it in momentum. But the surface has to be preserved. So it gives me this condition. And this transformation can be also performed exactly the same way in the quantum case. And in this case, it is called Bogoliubov transformation, and it was discovered by Bogoliubov and Valatin. And of course, it can be generalized to higher dimensions. So here we have one-dimensional example, but we can consider higher dimensions. And it is known that it can be used to diagonalize quadratic Hamiltonians as long as they are stable. So just as here we found the modes of a different system from this one, we can also do this in the quantum multidimensional case. if it is stable. So it's basically harmonic potential which goes up and not down. And the applications of this Bogolubov transformations are very wide. So it's used in quantum optics, superconductivity, Bose-Einstein condensates, Unruh effect, Hawking radiation, and many more. And here we will use it also for our purposes. So how we can use it? As I mentioned before, this system is quadratic. So we can use this Bogolubov transformation as long as our system can be expressed in such a form. So we have here a set of operators, bosonic operators. So the C contains both the light operators and matter operators. And as long as this is quadratic, we know that we can find Bogolubov transformation, which transforms the system into a set of normal modes, which are harmonic oscillators. And this transformation is given by this formula. And we don't know what are the coefficients of this transformation, but actually we will see that it's not necessary to know exactly this coefficients. What matters is the existence. So why does it matter? Because we can make a simple guess. So, you know, before in the photonic case, we had this simple-looking formula where the electromagnetic field operator and magnetic field operator were given just by the normal modes of the system. So now we do exactly the same, a similar guess. So we assume that our electric field operator is given by polariton operator times the shape of the normal mode of the system. And this normal mode contains both EJ component and XJ matter component. And additionally, we'll assume that these eigenmodes, E and X, are normalized in such a way that the value of the Hamiltonian functional is equal to H omega J, which will just simplify formulas. It's not a very important assumption. So if this is the case, we can actually check that these formulas are correct. Why? Because we can verify this by considering a classical limit and calculating a two-point correlation function for a coherent state. So if we have a system in a coherent polariton state, so a state which is eigenstate of the polariton operator with certain value alpha, then we can use this property to calculate a second-order correlation function. So first-order correlation function. So this correlation function is given in terms of electric field operators, E plus and I minus, which are positively oscillating and negatively oscillating part of the operator, which is this part and this part, respectively. And if we calculate this formula, we find that this is exactly the value that we expect for a eigenmode of Maxwell equation in the classical limit. So here is additionally we get number of particles in this coherent state that we consider. So, and we can check in this way using different kind of correlation function, so between different points in R, but also between E and X, to check that all these correlation functions are correct. And of course, no other coefficients in front multiplying these operators Pj will give correct correlation function. So this is the only combination that gives correct values. And we know that this transformation exists, so in this way we find the correct solution. Okay, so far I considered quadratic systems, but can we go beyond this, and can we consider systems which are not quadratic? For example, interacting like two-body interaction Hamiltonian. So this is an example, and actually it's also quite useful that we know this the form of this these operators because we can just insert them in this formula. And we can calculate the corresponding Hamiltonian contribution, which has such a simple form. So again, you see that there is a two-body interaction, and there is some coefficient for it, which is dependent on the overlap integrals of the exciton part of two modes. But as you can see, this Hamiltonian contains non-local interactions. So it means that there can be interaction between modes, which not just within one mode, but also between other modes, which can be important in some applications. Okay, so
this is relevant for excitons? This X to 4 Hamiltonian?
Yes. So actually, this is we took it because this is exactly the interaction that exists in polariton system. So this is like a contact interaction which is instantaneous, and excitons are very small compared to the wavelength of light. So it means that the interactions is practically on a there is some range of interactions between the excitons, but it is comparable to the size of the exciton. So usually you can just assume that this is just like a delta interaction. And yes, so I mean, I think almost always this kind of interaction is assumed, and it agrees with experiments very well. Okay, so now I will consider the dissipative case. Well, are there any other questions? So, would like to ask something? So maybe this, I don't know, maybe this is quite unusual formalism or something, but okay, so maybe I will just briefly go through this dissipative case. So in the dissipative case, what we want to consider is a system where, apart from this Hamiltonian part, it also has some dissipative part, which we assume to be Markovian and given by just simple Lindblad terms. So here because we were considering quadratic system, so here we need to have linear Lindbladians to still be in the quadratic regime. And so this kind of terms can describe decay, gain, but not the coherence without decay, for example. And so we will assume that no polariton mode is immune to decay. So the only steady state of the system, because we have no pumping here, so the only steady state is just the polariton vacuum. And what we want to achieve is to find a diagonal basis of eigenmodes. So this part is written already in the diagonal form, but this Hamiltonian part has in general a different diagonal basis.
So this coefficient C mu j have nothing to do with previous?
No, this exactly. So I assume that these are arbitrary. So for example, because usually the decay is not just decay polariton, but maybe decay of the photon or exciton or some other. So what we want to achieve is to have a common diagonal basis for these two parts. And it is actually what we need to do is kind of like perform a dissipative analog of this Bogolov transformation that I described before. And this is known under the name of third quantization. So it was introduced in 2008 by Prosen, and in the fermionic case, and then also generalized to bosonic case in this paper. And this is again some kind of new formalism, so maybe I will not discuss this in detail. But basically here we are now working on operators, like density matrix operator, and we are using super operators, so operators acting on the operators, just like the Liouvillean, to find the eigenbasis of the system, of the Liouvillean. Okay, maybe I will just skip it. But in the end, what we do, we can show that we can find an eigenbasis of this set of equations where now we have some dissipative terms as well. So we have some imaginary part of the dielectric constant. We have some decay of the exciton mode. And we also can have some absorbic boundary conditions in our computational model. And all of these things can contribute to decay. So this is a very similar problem, but of course different problem because it's non-Hermitian. But using this third quantization, we can finally show that, that our system is described by this familiar form of the Liouvillean. So the Liouvillean can be decomposed into normal modes. And now there is no mixing between different modes. However, the price is that these modes are now non-orthogonal. So care has to be taken when performing some computations, for example, to take this into account. But we can still find an eigenbasis. And what is very nice, this eigenbasis is exactly the basis of this Maxwell equation, classical Maxwell equation. So we need to solve only the classical equations, which are relatively easy to solve, to find the basis of the quantum system. And we can, for example, limit ourselves just to a few modes that we are interested in. Yes, so this I mentioned. So now we did some applications of these calculations. So what we considered is a system where we have exactly a microcavity, which is like translation invariant, but we have some limited region of excitons where the excitons can exist. And we just solved the classical Maxwell equations to find spatial distribution in eigenmodes of the system, including the effects of dissipation. And why we took the system? Because in the polariton community, there is a strong desire to find system where this interaction, so by interaction I mean the value of this interaction Hamiltonian, or expectation value, is stronger than the coherence. And it is very hard to achieve. So far, only some small non-classicality or related to this interaction was achieved. But if we had strong U, so U is the interaction coefficient that is stronger than the coherence, which is represented by decay constant gamma, we could have very non-classical effects. So you can see that according to our simulations, depending on this active layer size, so how big is this active layer, we can achieve actually this regime where this U is even 10 times stronger than gamma, and we are still in the strong coupling regime. So still this coupling between exciton and photon is stronger than the decay. So we have still polaritons. And another application that we thought would be interesting is try to design structures in a semiconductor which will exhibit this non-local interaction property, which may be interesting for some quantum simulation, for example, or quantum computing. And it is possible, and we propose such a structure where we have some like volume of material which is slightly different refractive index, which effectively traps light into these regions, as you can see. But the active region of excitons is in between them. And in this case, you have the strongest non-local interactions. So in the Hamiltonian that you get, you have a high value of this left-right interaction. It is comparable to this left-left and right-right interaction. And importantly, we have no fitting parameters at all, because all this refractive index and interactions, all these parameters are known in the literature, so we can calculate them exactly And yes, I think it's maybe the biggest advantage of this approach. Okay, so thank you for your attention.
Okay, thanks a lot.
I think it was really a nice talk. And we have time for questions. Yes?
On the last slide, what were these two white let's say boxes above the quantum well layer?
Here.
Yes.
So actually this, because normally we have layer of one semiconductor, another semiconductor, and here this white, it means that there is another composition of in the semiconductor which is here, but actually it should be the same color as this, because the refractive index is more or less the same here and here. So it means that in this structure we assume that we have layered structure, but here we have some kind of mesa or something like this, where this is filled with this aluminum O2 instead of aluminum 95.
And this wave on panel B, it's perpendicular, so is it going into the screen or it's parallel?
No, this is exactly in the same axis as here. So this is just zoom. So this region marked with a dashed line is exactly this region shown here.
And the tuning in panel D, so I guess you are tuning something in these two mesas, let's say, to change the.
Okay. Yes, I didn't say that. So actually, there is so in the simulations we assume that we have excitation laser with frequency which is detuned to the energy of this mode by some value delta, and this is.
And these two modes, left and right, are in resonance.
No, there is this. Okay, so yes. Okay, so it's more complicated. So if you diagonalize this system, which you get symmetric and antisymmetric mode. So what is shown here is symmetric mode, but antisymmetric mode looks exactly the same, but it has phase flipped by pi, almost exactly the same. And now what we do, we construct from these two modes, we construct left and right mode, but by a symmetric and antisymmetric combination of these two eigenmodes. They have slightly different energy, but the left and right, because they are just equal combinations, they have the same energy. So left and right have the same.
Okay, yes, Michał.
So I wanted to ask about the entangled photon pairs. What are the two modes in the end, and what parameters are they entangled in, and why it is interesting to produce entangled photon pairs? Why are they interesting?
Has anybody produced them in this way?
Yes.
Okay.
Yes, exactly. So they are produced by parametric down conversion, but maybe you could have a semiconductor device which does.
Parametric down conversion itself doesn't produce entangled photon pairs. You need two indistinguishable processes in the end.
Okay,
You
mean
two modes and some other degree of freedom in which the photons are entangled. Yes. So what are those modes here, and the degrees of freedom?
Yeah. So if you are asking what are the modes, then okay, imagine that if we talk about photon production, so imagine that you have this semiconductor system, and then you have optical system which can you can address the left and right mode, so like a lens with very fine. So then you put detector after this lens. So it's like a microscope, and so in this way
so that I have two modes. So then what is entangled between those two modes then?
So it means that if you detect, you have two special modes. So it's entangled between two special modes. So I don't know what else do you need to have entanglement. Is
Like polarization, for example.
No,
You have
but-
two beams and polarization, state of polarization, polarization entanglement. Yeah.
yeah. So there,
So maybe you are talking just about entanglement between excitations or some. I'm mode. So is it mode
no.
entanglement or photon entanglement?
okay, it's exactly the same entanglement as in parametric Dant conversion. So, but in parametric Dant conversion, you additionally have polarization degree of freedom. So
You don't need to have. Yeah.
no, yeah, you don't need to have. So if you want to have,
So this is entanglement between an excitation in one mode or lack of it, and excitation in the other mode.
okay, so there are. It doesn't matter if you talk about polarization mode or spatial modes. It's just a basis. So it's the.
But you measure in the end, and you see correlations between what physical
Yes,
properties.
yes.
But what physical properties you measure to see correlations that
So-
are a result
so-
of this entanglement?
So. So then you can construct so if you have this microscope device, then it kind of transforms this modes in the polariton to modes of the photons, which are flying modes. And then you know that photons in these modes are entangled. And then you can construct some interferometer, for example, first order correlation measurement, second order correlation measurement, and you can, by detecting the clicks, you can verify that these modes, photons in these modes are entangled. So it doesn't have to be polarization, but because polarization is just another, index that.
I need two labels.
Yeah, and
What
so
are the two labels?
so the label is the spatial mode label.
And the other one?
No, you just need one label.
I guess
Okay. Yes.
Yeah.
Maybe this is this entanglement due to symmetrization of photons as indistinguishable particles you are referring to. Okay.
I'm not convinced yet.
Okay, we can.
Okay.
We can talk about
Basia
it.
had a question. Yes.
No, but I have a simple question. So it's just the exciton that has to be confined in this blue region. Yeah. So you add additional confinement on the exciton itself. So
Yes.
excitons cannot be like 2D in the full possibility to move in the full quantum well, but only restricted to this mode. Yeah. to
Yes.
this
So
spatial
we are constricting excitons to this area, but photons can be everywhere. So, but excitons.
Yeah, so like a huge quantum dot, yeah, so in the limit between the small one and the big one. So you need sort of like the meso.
So normally you have excitons confined in the quantum well, which is like a plane, like a layer.
Yeah, and here you have to restrict it
And
additionally.
here you have additional restriction.
Because usually in the typical quantum wells we don't have that. Yeah, so usually we don't deal with any type of the confinement for the exciton. So that will be
Yes.
like a new structure, completely new structure that we have.
Yes. So the question is if it's how difficult it is to create constriction just for the excitons. This I don't know, but,
No, but it's by the growth. So you would need to make like the localized different material here. But this is possible. This is it's
Yeah, so-
sort of okay. But this is very super great. Yeah, this we can make.
Okay. So any other questions? Maybe on this side. I saw here some rumors. No. No questions. Sure. No more questions or any last question? Okay, but so I didn't catch whether this is already experimentally
no.
done. No, it's just a proposal.
This is just a theory. Yes.
Okay, so it may not work in the end.
Yes, of course.
Okay, but let's hope it works. Okay, so let's thank Michał again.
Okay.